of the puzzle-like fit of the continents. And Alfred Wegener just didn't have access to that in 1912. So when he moved forward with actually publishing his idea, he published it in 1915. The science community basically laughed at him. They said there is no way that these massive pieces of land, our continents, are able to move. Where they are today is where they have been throughout time. That there's no physical mechanism that would allow for the continents to move. That they've been stagnant where they currently sit. That's where they always have been. And there's no way that they were once one giant landmass. That's what the scientific community said in the early 1900s when Wegener proposed this idea. And really, it was because of the lack of evidence. Wegener just had the puzzle-like fit. That was his only piece of evidence for continental drift. That's not enough evidence to come up with a theory, okay? So remember from last class, we talked about the scientific method, and eventually, if you get the same result over and over and over and over again, you can come up with a theory. Wegener didn't have enough evidence to come up with the theory, but he was proposing this idea, okay? All he could base things off of, puzzle-like fit. He didn't understand the physics behind it. He didn't know how this was going to work, how the continents actually move. It's not possible. At that time, they didn't think it was possible. So later on, when we started to develop that computer technology to show the actual true movement of the continents and how they truly do fit together like a puzzle piece, we started to revisit this idea. So in the mid-1960s, 1970s, 1980s. But they wanted more evidence to help prove this idea of continental drift. They couldn't just base things off of a puzzle-like fit. So through the computer modeling, one of the things that they noticed is when you started to put the continents back together into those puzzle pieces and putting them back together where they should go, what they saw was the mountain chains. If there's a mountain chain that was in one continent, and then as you move the next continent next to it, where that puzzle-like fit would occur, the mountain chains would be continuous. The mountain chains would match up. Okay, so you would get this continuous mountain chain. So a good example is here. Okay, you can see North America and Europe. You can see the mountain chain running along the east coast of North America. And where it fits into Europe, the mountain chain continues. So now we've got another piece of evidence. We've got the puzzle-like fit. We've got the continuation of mountain chains. Okay, the next came with rocks. Okay, what we did was we took samples of rocks along the coastlines of where the puzzle-like matches occurred, and you saw the exact same rocks in terms of type, what they're made up of, and the exact same ages of the rocks. Okay, so a rock along the coastline of South America where it matches up into Africa, those rocks are exactly the same age, exact same composition. That would only occur if at one point in time they were connected. Okay, you would have something that was a variance within the rocks if the continents were always sitting where they are today. They might be a different age, they might have a little bit of a different composition, they would not be exactly the same. But what we saw was the rocks were exactly the same along different coastlines and different continents, but where they would match up in that puzzle-like fit. So now we've got three pieces of evidence. We got the puzzle-like fit, we got the matching mountain chains, and we got the same rocks. Next came with glacial evidence, okay? So as we were developing new technologies and starting to rely more on oil and things like that, we would do digging explorations, really for oil. But what we saw was when you dig down in Africa and you dig a little bit further down into the ground, you see a lot of glacial evidence. And it's too much glacial evidence for it to occur during an ice age. The only way to have that much glacial evidence is that Africa had to have been further south than it currently is today. Okay, so like in the middle of Africa, you've got desert-like climates. Okay, you wouldn't expect to find glacials there or glacial evidence there. But if you dig far enough down, you do. And like I said, it's too much evidence. There's too much of it to have occurred during an ice age. The only way to have that much glacial evidence is that Africa had to have been further south than it currently is today and moved where it currently sits. So now we've got puzzle-like fit, we've got the matching mountain chains, we got the same rocks, We got glacial evidence in Africa that you just wouldn't expect to find unless Africa was further south than it currently is today. Next was fossils, okay, organisms. In particular, there was a lizard that they found. They found the fossils along the coastline of South America and also along the coastline of Africa. And it was the exact same organism, same age, same body structure, same bone composition. Everything was exactly the same, exact same organism. Now, you would think that's not unusual, but when you have the exact same fossils, okay, along the coastlines in two different continents, that actually tells us it's another piece of evidence that the continents worked together at one point. A good example of modern day squirrels, okay, there's squirrels all over the world, but they will have a slightly different body structure depending on where they are in the world, okay? They're still squirrels, but their body structure is going to be a little bit different if they're in North America versus South America, because it's different climates, they're going to have different food sources, whatever it is, they're going to have a little bit of a different bone structure to them. But for us, we found the exact same organism to a T in South America and Africa. So that's another piece of evidence of continental drift. You wouldn't expect to find the exact same organism on continents separated by the Atlantic Ocean like that, okay? So we've got puzzle-like fit, same rocks, continuation of mountain chains, we've got the fossils, and we've got glacial evidence in Africa, okay? So we're up to 5 more pieces of evidence of continental drift, okay, to help prove Alfred Wegener's idea. But again, he didn't know any of this. He didn't have access to any of this when he wrote his article in 1915. This was all newer findings in the 60s, 70s, and 80s. Some of it actually stems from World War II. Some of the evidence that we eventually found stems from World War II. This was something we didn't realize during World War II, but it's something we revisited after World War II. So during World War II, we developed some new sonar technology. Sonar is when you send a sound signal down into the ocean, it hits some sort of feature on the ocean floor and bounces up to a receiver. In the time it takes for that sound signal to go down and return, you can start to get a picture of the ocean floor that way, okay? And this was very early primitive sonar equipment. So it wasn't exactly the clearest pictures. We developed it to find German U-boats, okay, German submarines, but there's not a German submarine in every single part of the Atlantic Ocean. So we accidentally did a rough map of the Atlantic Ocean floor during World War II. And we started to see some unique characteristics on the floor of the Atlantic Ocean. So eventually, after World War II, again, 60s, 70s, and 80s, they started to go to the bottom of the Atlantic Ocean and look at these unique features, okay? And one of the things that they would look at when they would go down to the bottom of the Atlantic Ocean is the polarity, okay? Whenever Earth has a polarity to it. So if you ever go hiking or you're in the backwoods and use a compass and you point the compass north, you're pointing to the magnetic North Pole. That's Earth's polarity. That polarity at that time gets imprinted into rocks that are being formed at that time, okay? The polarity of Earth shifts over time. It's called paleomagnetism. So what actually happens is, it's called polar wandering as well. It's just another term for it. Earth's polarity actually changes. We don't know why the magnetic polarity of Earth changes. We have no idea. But about every 20,000 years, when you're holding your compass north, Earth's polarity shifts and you would actually be pointing south, okay? You're not pointing to the North Pole. You'd actually be pointing south. So that polarity of Earth, whatever it is at a given time, gets imprinted into rocks. And that's one of the things that we measure when we were starting to look at some of the unique features of the ocean floor from that sonar that we developed during World War II and accidentally mapped the Atlantic Ocean floor. So this is the magnetic North Pole. So you can see how it shifts over time. So the true North Pole is to the upper right-hand corner, but the magnetic North Pole is to the west of that. okay? Sometimes it's to the south of it and to the west. That's the polar wandering. That's Earth's polarity shifting over time. So a rock that's formed in the early 1800s, the polarity that gets imprinted into that rock is all the way at the bottom, okay? That dot all the way at the bottom in this line graph. Whereas a rock that's formed in 2020 is going to be all the way at the top in the middle, okay, that line graph. So you can see how the polarity of Earth is shifting over time. That's what's getting imprinted into those rocks, and that's one of the things we can measure. Again, we don't know why the shifting happens. It just does. So again, in about 20,000 years, when you're holding your compass north, you're actually going to be facing south, okay? That's the shifting of Earth's polarity. So again, another name for it is polar wandering. But how does this play into evidence for plate tectonics? And I'm going to get into that, okay? And it has to do with some of the measurements we took. Or if I say plate tectonics, I'm also saying continental drift. They're interchangeable. Sorry if I wasn't clear on that. Plate tectonics and continental drift mean the same thing. So how does the shifting of polarity play into evidence for continental drift plate tectonics? So what it actually tells us is when we went to the bottom of the ocean, bottom of the Atlantic Ocean, and started to take some measurements, we saw a really unique feature in the Atlantic Ocean. There's a huge mountain chain that runs directly in the center of the Atlantic Ocean, north to south. It's actually the world's largest mountain chain. We call it the Mid-Ocean Ridge, okay? So that's one of the unique features that we wanted to study, was why is there this huge mountain chain in the middle of the Atlantic Ocean, at the bottom of the Atlantic Ocean, running north and south? So we would go down there and we would take samples of rocks, okay? And what we saw was rocks that sit exactly on the mid-ocean ridge were just forms. So what that tells us is that there's material from inside planet Earth coming up and escaping at the mid-ocean ridge like a volcanic eruption, and then instantly cooling and forming a new rock, okay? And then Earth's polarity at that time, when that rock was formed, gets imprinted. If you go equal distance to the west and to the east of the mid-ocean ridge, what you see, the rocks are a little bit older, okay? So the rocks, if you look at this graph or this picture all the way at the bottom left, the rocks in the red, okay, those are brand new rocks, and they have the current polarity of Earth. The rocks kind of in like the middle, and it's kind of an orangey color. Those rocks are a little bit older than those in the red, okay? But the rocks in the orange, equal distance to the west and east of the mid-ocean ridge, are the exact same age, okay? They're older than the ones in the red, though. But they also, the ones in the orange, exact same age, exact same polarity. So that tells us they were formed at the mid-ocean ridge and then moved to the west and moved to the east, okay? So something's driving that movement. And again, if you go even further to the west and to the east, this more yellowy orange color, those rocks are even older. They're older than the ones in the orange. They're older than the ones in the red. But equal distance to the west and to the east, the ones in the yellow-orangey color, those rocks are same age and have the exact same polarity, okay? Different polarity than the ones in the orange, different polarity than the ones in the red. But it's telling us, again, the rocks are being formed at the mid-ocean ridge, they're falling down it, and then they're moving somehow to the west and to the east, okay? So this movement, it's telling us that it's possible for land to move, okay? Because the ocean floor, it's going to push things to the left or to the west, and it's going to push things to the east. So anything that's sitting above that ocean floor is moving with it, okay? But how is it moving? That we didn't know. We knew that it was moving. This is proving that movement, okay? It's adding to the evidence of continental drift plate tectonics, but we didn't understand how is that actually happening. We just knew that things were moving, but how are they moving? So Harry Hess, who was one of the submarine captains during World War II, He's the one that went back. He saw these unique features on the Atlantic Ocean floor, and he's the one that started to kind of go down there and study it and try and figure out what's going on. And what he did was he came up with the idea of how this is actually moving. How are things actually moving? He called it seafloor spreading. Okay. Basically, what he said was inside planet Earth, we have the different layers that we talked about last class. We've got the crust, we've got the mantle, and we've got the core. The crust is the least dense. That's the part we walk on. The mantle is a little bit more dense. The core is the most dense. Okay. But we know we have a liquid core. Okay. So liquid core. What's happening is inside planet Earth, the heaviest or most dense material is falling down to the core, the center of planet Earth. That material, whatever it is, it's mainly iron, but when you sink all the way to the bottom, okay, all the way to the core, gravity's pulling down on you, all the high density material is going to fall to that bottom level. That material is going to get pushed together, and they're going to start rubbing up against one another. So if you take your hands and rub up your hands against each other and you start rubbing, what you're doing is you're generating friction. When you generate friction, you generate heat. So that material that's fallen to the core, gravity's pulling it together. They're going to start rubbing up against one another, generating friction, which is going to generate heat. There's enough heat that's generated, that material is going to start to melt. Okay? That's why we have a liquid core. All that high density materials fall into the bottom. Gravity's pulling it together. They're going to rub up against one another, generate friction, generates heat. That's going to cause the material to melt. When you melt something, you are going to make it less dense. The less dense you are, the further up you want to be. So that material is going to try to escape. So the material from inside the core is going to shoot up through planet Earth and try and escape through the mantle and then through the crust. It's going to try and seek somewhere to escape. So the core material, again, high density material fall into the bottom of planet Earth. The gravitational attraction is going to pull them together. They're going to rub up against one another, generating friction. That's going to generate heat, melting the material. When you melt something, you make it less dense. So the material shoots up through planet Earth, looks for an escape. Where it escapes is that mid-ocean ridge, that huge mountain chain in the middle of the Atlantic Ocean. It's basically a huge chain of active volcanoes. That material, as it escapes, it hits the ocean. The bottom of the ocean is very cold. It's like 34 degrees. So the second it hits that water, it's going to instantly cool and it's going to solidify. That's rocks, okay? This is one of the ways that rocks are formed. So it's all escaping or trying to escape through a very small space. Not all of it is going to be able to escape. Some of it's going to get stuck. Now, it's still going to be cold enough where it's trying to escape that the material starts to solidify again. And as it starts to solidify again, even though it's stuck and can't quite escape through that mid-ocean ridge, it's going to fall back down into planet Earth, okay? Because it's starting to solidify, becomes solid again, it's going to become more dense. That material is going to fall back down towards the core. And then the cycle continues. It's going to go to the core, remelts, go back to the surface, try and escape. Not all of it gets to. Some of it's going to start to solidify again, fall back down, and you get this cycle. It's what we call a convection cell, okay? It's high density material melting, forming low density material, trying to escape through Earth's crust. Not all of it's able to. Some of it gets stuck, still starts to solidify because it's still colder up there, and will fall back down. And then the cycle continues, okay? So you get this constant flow of material. So material's constantly escaping through that mid-ocean ridge, okay? But the material that doesn't get to escape, as it starts to solidify and fall back down, it's going to pull these things called plates that we sit on top of with it, okay, these plates are basically like big slabs of rock that we sit on top of. They're going to get pulled with the material that's trying to escape, that wasn't able to, and is falling back down into planet Earth. All right. Does that make sense to everybody? Does anybody have any questions about that? No? Okay. So as that plate is getting pulled, this gray kind of slab here, that plate is pulling the land above it with it. So that plate is what's driving the movement of the rocks away from the mid-ocean ridge, okay? Either equal distance to the west or to the east, okay? So that's the driving mechanism of continental drift, of plate tectonics, is this convection cell within inside planet Earth. So the mid-ocean ridge, that's the area that we call a spreading center. That's where the new rocks are being formed. Subduction zones are areas where material is falling back into planet Earth. And we'll go over subduction zones and what those generate here in a minute. Okay, here's just another picture dictating the ages of rocks and showing that spreading effect. Okay, we already went over this. It's just another picture showing you that the rocks right at the mid-ocean ridge, where that magma is, where that picture of the magma is, that's the mid-ocean ridge. The rocks right at the mid-ocean ridge, young rocks, brand new. Those in the purple, a little bit older, okay? And then those all the way to the left and to the right, those are the oldest rocks. But as the material's trying to escape, it's going to pull the land with it, okay, that is sitting above those plates. So we also started doing, when we were doing the exploration and doing the studies of the ocean floor, one of the things that we looked at were the ages of the ocean floor. You can calculate the ages of rocks and things on the ocean floor, and what we saw was the oldest ocean floor is only 180 million years old. Earth, if you remember from last class, is about 4.6 billion years old. So the ocean floor is relatively young compared to how old Earth is. So what that's telling us is that Earth's ocean floor is constantly being recycled. We're getting the destruction of older ocean floor, but the formation of new ocean floor. And it's just a constant cycle, all because of this convection cell that's happening here. So this map here is showing the ages of the ocean floor. Those in the reds and all the way into the yellows, those are the youngest parts of the ocean floor. Those in the brownish areas, those are the oldest ocean floors. So anywhere where there's like this really dark red color, that's the youngest ocean floor. Those are mid-ocean ridges. Those are spreading centers. Those are where we're getting the formation of new ocean floor that is allowing the material from inside planet Earth to escape. Those in the browns, those are typically subduction zones, okay? Those are typically areas where the ocean floor is falling back down into planet Earth and being destroyed. All right, don't worry about heat flow, okay? You don't need to know about this slide. So typically, where there's certain earthquakes, okay, those earthquakes tend to occur at subduction zones, okay? Not always, but most earthquakes occur at subduction zones. Subduction zones also occur where what we call plate boundaries, which I'll go over here in a second. So all these red dots you can see are different earthquakes, okay? You can notice here in South Florida, there's not really any red dots there. And there's a reason for that. We don't really have to worry about earthquakes, okay? And it's because of the plates that sit underneath us. So underneath our crust, there is a series of these big slabs of rocks that we call plates. And there's multiple plates underneath us, okay? So in North America, we sit under, what's underneath us is the Caribbean plate, okay? It's also part of the North American plate, but it's mainly the Caribbean plate. So you can see all the different plates that are underneath planet Earth in all these different continents. The arrows are showing which direction the plates are actually moving as well. But you can see that there's multiple plates underneath us, okay? These big slabs of rock. These are what are moving through that convection cell. And that movement of the plates is what's going to drag the continents with it, because those continents, our continents, sit on top of these plates. So whenever the plate moves, the continent moves with it, okay? The driving force behind all of this movement is right in the Atlantic Ocean. That mid-ocean ridge, the mid-Atlantic ridge, that's the primary driving factor. It is the strongest force of all of the movement, okay, is right at that mid-Atlantic ridge. So the plate tectonics theory is basically just the more advanced idea of continental drift. And it's actually explaining how the continents moved through that convection cell. So what it's saying is within our lithosphere, okay, if you remember, we talked about the physical layers as well last class. Within the lithosphere sits these tectonic plates, these big slabs of rock. And then underneath the lithosphere is the asthenosphere, and it's kind of plasticky, okay, which allows movement. And because the asthenosphere is kind of plasticky, these plates are allowed to move all due to that convection cell. Let me go back to that slide. Okay, all through this convection cell, okay? Without the asthenosphere being plasticky, the plates would be stuck, and the plates would not be able to move. But because the asthenosphere is kind of plasticky, anything within the lithosphere is able to move. Okay, so the plates, they sit within the lithosphere and they're able to glide along the asthenosphere because of that plasticky composition. Okay, so this map again shows all the different plates, and you can see how many plates there are. And you can see that all the plates are touching each other, okay? Some plates are touching multiple plates, some are only touching one. It all depends on which plate you are. But you can also see that arrows are showing different types of movement. Some are spreading apart, they're moving away from each other. Some are moving right into each other, that they're moving into the exact same spot. Some, they're sliding past one another, okay? So wherever the plates are touching each other, wherever we have two plates touching each other, that's what we call a plate boundary. And depending on the type of movement that is occurring, will determine what type of plate boundary we have. There's three different types of plate boundaries. And we're going to go over all three of these, okay? So you don't need to write them all down. I'm going to go over each one of these. The first one, the top one, is what we call a divergent plate boundary. The middle one is what we call a convergent plate boundary. And the bottom one is what we call a transform plate boundary. So the top one, the divergent plate boundary, is two plates that are touching that are moving in opposite directions. They're moving away from each other. That spreading center, okay, that mid-Atlantic ridge. The middle one, convergent plate boundaries, that is two plates that are moving into each other. They're colliding head on. And then the bottom one, the transform plate boundary, is two plates that are sliding past each other, okay? So depending on the type of movement, wherever those plates are touching, the type of movement that they have, that will determine what type of plate boundary they have. The type of plate boundary that they have will also determine what type of geological features or events are going to occur. So this table here is the rest of the lecture, okay? So if you understand this table, or if you know this table, you understand all the slides that are about to come up. So we're going to start with divergent plate boundary. These are two plates moving in opposite directions. They're moving away from each other. So when you have two plates moving away from each other, okay, in opposite directions, what you create is a void of space. And then that material from inside planet Earth is allowed to escape, okay? So divergent plate boundaries, that's the mid-ocean ridge. That's where you're going to get those new rocks being formed. So back to the map, right here in the Atlantic Ocean, that huge mountain chain, okay, you can see the arrows moving in opposite directions. That's a divergent plate boundary. It allows for new material from inside planet Earth to escape, generate new rocks. The plates are moving in opposite directions. It generates a void of space, allowing for the materials to come in and fill that space. The material from the core to come up and fill that space. So you're going to generate the new rocks here. So mid-Atlantic ridge, mid-ocean ridge, divergent plate boundary. Typically, the earthquakes here are pretty small. Sometimes the material, as it's being formed and it's coming out, it can cause some seismic activity. They're typically not very big, okay? Very, very small, focused earthquakes. So again, divergent plate boundary, okay? Two plates spreading apart, you get a void of space, material from inside the core is allowed to escape, okay? And then you generate new material there, and then as the plates move, they're spreading apart. All right, types of spreading centers. I put it in here, you don't need to know this. This is really at just basically how fast the plates are moving apart from each other, what type of spreading center you have. You don't need to know about oceanic rise, oceanic ridge, or ultra slow, the types of spreading centers, but I put it in here just in case you wanted to see that there are different types of these divergent plate boundaries depending on how fast they're moving away from each other. All right, next is convergent plate boundaries. This is when two plates are moving into each other. They're colliding, they're converging, okay? So this is where you're going to have some unique geological features occurring. And it depends on what types of plates are colliding. There are two types of plates on planet Earth, okay? We have multiple plates. Again, I'm going to go back to the map. These plates are the plates, okay? We have distinguished plates underneath us. But depending on what's above them determines what type of plate you are. If you have water above the plate, you are what we call an oceanic plate. If you have land above the plate, you're what we call a continental plate. You can be both. So like the Caribbean plate, North America sits on top of the Caribbean plate. So if you're standing in Miami, you're standing on the Caribbean plate. Okay, you're going to Miami Beach, you're standing there, you're standing on a continental plate specifically. The second you put your feet in the water, you're still on the Caribbean plate, but now you're on an oceanic plate. So it depends on where you are located to determine what type of plate you are, okay? So that's going to determine what's going to happen with these convergent plate boundaries. Is what types of plates do you have colliding? So again, there's three different types of convergent plate boundaries, and I'm going to go over each one of these. The top one is what we call an oceanic continental convergent plate boundary. I have an oceanic plate colliding with a continental plate. The middle one is called an oceanic convergent plate boundary. I have an oceanic plate colliding with another oceanic plate. And then the bottom one is what we call a continental convergent plate boundary. I have two continental plates colliding into each other. So depending on which type of convergent plate boundary I have will determine what type of geological feature or geological event I'm going to have occur. So we're going to start with the oceanic continental convergent plate boundary. I have an oceanic plate colliding with a continental plate. So I have a plate with the ocean above it colliding with a plate with land above it. And they hit each other, okay? They're moving in the exact same direction and they hit each other. When they hit each other, one of the plates wants to give, okay? One of them wants to subduct. It wants to go back down into planet Earth. If you remember from last class, we talked about that there's two different types of crust. There's oceanic crust and there's continental crust. Oceanic crust is more dense. It's the same thing with plates. Oceanic plates are more dense. The more dense you are, you want to go down. So the oceanic plate is going to be the one that gives, and it's going to sink, and it's going to subduct, and it's going to go back into planet Earth. So a good example of this is Washington State. Washington State sits on top of an oceanic continental convergent plate boundary. So the last major volcanic eruption that occurred in the continental United States was at Mount St. Helens, which is in Washington State. Mount St. Helens is the result of an oceanic continental convergent plate boundary. When the oceanic plate hits the continental plate and the oceanic plate gives and it subducts, that oceanic plate is going down into the deeper parts of planet Earth where it's hot down there. Okay, the material, gravity is going to pull it together. There's friction. there's heat, it melts. So that oceanic plate, as it subducts, it's going to melt. If that oceanic plate subducts too quickly and it melts too quickly, that material is going to want to escape as fast as possible. It's going to rise, it's going to shoot up through planet Earth as quick as possible. It can actually shoot up fast enough, and there's so much heat involved with it that it can burn a hole through planet Earth and start to collect underneath planet Earth in what we call magma chambers. Eventually, those magma chambers can no longer hold the material that's underneath it, and you can get a volcanic eruption. That's what happened at Mount St. Helens. So at Mount St. Helens, the oceanic plate subducted too quickly, and it melted too fast. And all that material had to escape, shot up through planet Earth, burned a hole through planet Earth, and then it started to collect in those magma chambers. Eventually, the magma chambers couldn't hold it any longer. Mount St. Helens erupted. Okay, so that's one way you can get volcanic eruptions. Okay, one way. Next, we have the oceanic convergent plate boundary. Two oceanic plates colliding. Whichever oceanic plate is older, has the oldest material, the older the material, the more dense you're going to be. So the older plate is going to be the one that subducts. It's going to go back down into planet Earth and eventually melt. So in this situation, this is how you get trenches, oceanic trenches. The Mariana Trench. The Mariana Trench is an oceanic convergent plate boundary. Next, we have continental convergent plate boundaries. Plate with land above it, another plate with land above it, colliding. These plates are the exact same density. So instead of one of them subducting, they both fight for position and they push upwards. And when they push upwards, they push the land upwards. So the Himalayas, which is the largest mountain chain, it contains Mount Everest. Okay, Mount Everest sits at a continental convergent plate boundary. These land is constantly getting pushed upwards. Two continental plates colliding directly into each other, push upwards. Mount St. Helens is going to grow because of that. Mount St. Helens, it's only going to grow an inch, maybe a year, if that. But Mount St. Helens is going to grow because it sits at a continental convergent plate boundary. So you'll see that I have YouTube videos listed on some of these slides. These are videos you can go check out on your own time after class if you want. It's just more material to kind of go over these things again. So all the links should work. If some of the links don't work, let me know and I can send you the updated one. But you're free to go on your own time to check out these YouTube links. But this one in particular is going to go over the Himalayas and Mount Everest and how it's constantly growing because of its continental convergent plate boundary. All right, the last type of plate boundary, transform. These are two plates that are sliding past one another. Doesn't matter if it's oceanic, continental, oceanic, continental, transform plate boundaries. They all do the same thing. Two plates sliding past each other. These plates are not smooth. They're jagged. They have edges to them. Sometimes they get caught against each other, but they still want to slide past one another. So there's a lot of force there. There's a lot of friction being built up. Eventually, one of them is going to break. And when that plate breaks, part of it breaks off, you can get a major earthquake that way. So most major earthquakes are the result of transformed plate boundaries. So like California, it sits on what we call the San Andreas fault line. It's just a transformed plate boundary. It's two plates sliding past each other. They're not smooth, so they get caught sometimes when they're sliding past one another. Eventually they break, and then you can get an earthquake that way. So if you go back to the map, the reason here in South Florida, we don't have to worry about earthquakes, we sit over a single plate. We're not close to these plate boundaries, okay? So that's really one of the reasons we have very little to worry about with earthquakes. We might feel an earthquake because you can see the Caribbean plate does have a transformed plate boundary south of us. So we might feel some of the effects of an earthquake, but a true earthquake forming right underneath us, it's very, very unlikely. We also don't have to worry about volcanic eruptions. We don't sit anywhere close to a continental or an oceanic continental convergent plate boundary. So we don't have to worry about those geological events occurring because we sit on top of the plate. We're not close to a plate boundary. All right, so those are the plate boundaries, okay? So transform, again, typically that's how you're going to get your major earthquakes. Now, the one other example of geological features that I want to talk about is what we call hotspot. So hotspots occur in the middle of plates, okay? So in the United States, the only other area that we have active volcanoes is Hawaii. And there's only one active volcano in Hawaii, the Big Islands, okay? The Big Island of Hawaii is an active volcano. All the other islands, they don't have active volcanoes, just the Big Island. The Big Island sits on top of a hotspot. There are certain areas on planet Earth where the core is releasing so much heat at a rapid rate that it actually burns a hole through the plates, burns a hole through planet Earth, and it starts to build a volcanic island. Okay, so it's similar in terms of the oceanic. Let me get back to it. It's similar to this oceanic continental convergent plate boundary, where if it does melt too fast, it'll burn a hole through planet Earth. But the uniqueness of a hotspot is it's not at a plate boundary. It's in the middle of a plate. It's just a unique area where Earth is just constantly pumping so much hot material through it that it burns a hole through it and eventually generates this volcanic islands. So Hawaii, these are all the different hotspots on planet Earth. So like Yellowstone National Park, if you ever go there, Old Faithful, the geysers, that sits at a hotspot. It's not a strong enough hotspot where it's going to burn a hole completely through planet Earth, but it's strong enough to burn a hole and boil the water above it. That's where you get those geysers. But Hawaii is strong enough to burn a hole through planet Earth, generate the volcanic islands. So Hawaii, the big island, sits on the hotspot. But because of plate tectonics, Maui used to sit on the hotspot. And then Maui, due to plate tectonics, the plates are moving in the north to the northwest. Maui eventually moved off the hotspot. You got a new Hawaiian island that formed after, the Big Island. Kauai, same thing. Oahu, though they used to sit on the hotspot. And then eventually they moved off of it. New islands were formed behind it. So at certain points of history, Oahu, okay, wasn't there. Kauai was there at the hotspot. There was no Oahu, there was no Maui, there was no Big Island. As Oahu or as Kauai moved off of it, Oahu was formed. And then as Oahu moved off of it, Maui was formed. As Maui moved off of it, the Big Island was formed. There's going to be this constant generation of new Hawaiian islands. It's going to take millions of years for this to happen, but eventually what's also going to happen is like Kauai is going to fall back into the ocean. This is, again, millions of years. This is not going to happen tomorrow. This is going to take a long time. But Kauai is just constantly getting hit by the Pacific Ocean now. It's got erosion occurring. It's breaking apart. Oahu's constantly getting hit by the Pacific Ocean. It's constantly being broken apart. They don't have a way to replenish that land. So they're going to fall back into the ocean. But Hawaii is constantly going to generate new volcanic islands behind it. Okay? So over time, eventually there will be new Hawaiian islands. So this is kind of the life cycle of those volcanic islands. It starts off as a seamount as it's being formed. The second it sticks out of the water, it's a volcanic island. And then as it's falling back into the ocean, that's what we call a table mount. That's the basic life cycle of these volcanic islands. All right, so we can also detect continental drift, plate tectonics through satellites now. Basically what we do is we take a picture of planet Earth utilizing satellites, and then every year, every 5 years, every 10 years, we take another picture and we calculate, okay, this is the new location of the continents because we're constantly moving. We're moving right now. We're moving to the west, okay? Okay, the United States, North America, everything is moving to the west. Because the Mid-Atlantic Ridge, that divergent plate boundary, that is the driving factor for all of the other plates. It is the strongest feature. It's the strongest movement pattern. It's going to push everything to the west and to the east. So what's going to happen is in about 50 million years from now, Florida is actually going to be over by Texas. Okay, where Texas currently sits, that's where we will be in about 50 million years. In about 200 million years, what's going to happen is North America and Russia, we're going to slam into each other, and we're going to have a reverse Pangea. So in 200 million years from now, there's really going to be not much of the Pacific Ocean left. The Atlantic is eventually going to be the biggest ocean that we have. But that's hundreds of millions of years from now, and that's if Earth survives until then. Okay? So that's it for the lecture. Does anybody have any questions about chapter 2? All right. So before I let you go, let me share my screen. Okay, so for chapter 2, there's 2 assignments, okay? The first one, chapter 2 quiz, okay? It's the exact same setup as chapter 1 quiz, all right? It's 15 questions, it's timed when you're ready to take the chapter 2 quiz, all right? It's due a week from tonight by midnight. So when you're ready to take it, it's there for you. The one thing I want to show you, though, for chapter 2 is the homework assignment. It's a little bit different. It's an actual homework assignment. So your chapter 1 homework assignment was to meet your classmates. So for the chapter 2 assignment, when you're ready to do it, there's a section here that says chapter 2 homework, okay, under modules. When you click on that, you're going to go here. There's 4 questions, okay? These 4 questions are based off of the PowerPoint. Most of the information is there within the PowerPoint. You might have to look a little bit outside of your PowerPoint, okay? You might have to use an outside source a little bit. If you do use an outside source, just make sure you cite it properly. But for the most part, you should be able to answer 99% of this without having to use an outside source. So what you're going to do is you're going to answer these 4 questions. The way you need to do this is when you're ready to do the chapter 2 homework, you just click Start Assignment. You can either answer the 4 questions in a Word document outside of class or outside of Canvas and then attach it. Or you can just put your answer in this text entry section here, okay, where it says text entry. You can put your answers here. So again, you can either do it as a Word document, upload it here, or put it in as a text entry. And then when you're ready to do it, you just hit Submit Assignment. You're done. Now, in terms of the questions themselves, I like bullet points. I like short, to the point, very basic answers, okay? You don't have to go super, super detailed. You just need to get the gist of the answer. You're good, all right? You don't need full sentences. I like bullet points, short, sweet, to the point, okay? Does anybody have any questions about that? All right, for those that don't have any questions, you're free to go. Everybody else, I'll stick around and answer anything that comes up.